In the previous video, we discussed the theory of how we are able to transform a public key into a public key hash and then into a wallet address that has error protection using a checksum and the base 58 check encoding, and also vice versa, to be able to having the wallet address to get back the public key hash and also to check for errors. So now in this video, I'm going to focus on the programming part. I'm going to be using again Rust. And of course, the first step is just to create a new package for our code. So I'm going to go to my terminal and using cargo, let's create a new package called wallet address. Okay, so we have now a new folder created, wallet address, and we can open this with VS Code. Okay, so as you can see, we have here the main.rs file to start coding. So even before we start coding, this is going to be connected to a previous video as well, where we discussed digital signatures. And so now we know what crates are we going to need for, first of all, create the private key and the public key. That's the very first step, to create that pair of keys. So the libraries that we need right now are going to be the crates K256 with the features ECDSA and SHA-256 enabled, and also the crate rand_core with the feature getRandom. I'm going to just do it in one step. If you want to know in detail, you can go to that previous video while I go through step by step. In this case, we're going to just go to cargo.toml. And in here, I'm just gonna add, okay, we need K256, and we need the version which is the latest. It's 0.5.10. And then we have to enable the features that I mentioned before, which are ECDSA and SHA-256. All right, that is for this library. The next library that we need is the rand_core. And again, the version is the latest. For now, that is 0.5.1. And we need one feature to be enabled, and that feature is called getRandom. Okay. All right, we have the libraries, we have the features enabled. So now we can go ahead back to our main.rs and start creating this public and private key. Again, we did this before, so you can go to that video to check it out in step by step. But for now, I'm just gonna import what we need or bring into scope the things that we need right now. So from this library, we're gonna go to this module, the ECDSA. And we're gonna bring I believe these are structs, signing key. Yeah, this is struct, and the other struct is the verify key. So signing key is for the private key, verify key is for the public key. Good, and from the other package, we are gonna get the OS random number generator, or RNG, which is the one that's going to create this initial seed that it needs to be random, so that way there are no two public keys the same. So now in main, we can go ahead and create the first variable, the private key. And this is going to be equal, just close this for a moment, equal to, so we're going to use the signing key struct with the associated function random. And this one expects the OS random number generator. So, and it expects this to be a mutable reference or a mutable borrowed, as Rust used to call it. So a mutable borrowed of OS RNG. Okay, that gives us the private key. And now with the private key, we can derive the public key. So public key, it's equal to, we use this struct with the associated function from, and here we're gonna pass a reference. We're gonna a reference to the private key. So an immutable reference to the private key. But this time, what I want to get back is just the array of bytes that's describe the public key. I don't need anything else. I just want the very basics. So we can use this method toBytes. So to verify that it's working well and to start building some kind of a log of what we're doing, let's go ahead and trying to print some information in the console. So we use the macro print line. And let's see. So first of all, we have, this is the public key, right? We're gonna short as PK. And we want to see how many symbols does it have. In this case, how many hexadecimal number, because this is how it's gonna be represented. We are gonna want to see the size in bytes. So let's give it a name to this placeholders. I'm just gonna call this count. This is gonna be size, and it's in bytes. And then we're gonna display, first of all, the hexadecimal value, and below that, the actual array of bytes. So you can see both at the same time. So in the next line, I'm just gonna add the hex, and then below that, we're gonna add the array of bytes. In this case, with this debug format, because arrays, they need to use this format to be displayed. So now we pass the variables to the print line. And one thing, okay, so the count, as I mentioned, is gonna be how many symbols do we have there. But this is symbols in the hexadecimal number. Right now we have is an array of bytes. So we need a way to encode those bytes into hex. So a very simple way to do this is just by using a crate that is gonna do that conversion for us, or that encoding. And that is the crate called hex. So we're gonna go back to Kaggle.toml and say hex equal. So we need the version 0.4.2, which is the latest right now. And with hex, we can actually just import it, and it's gonna give us access to these handy functions. All right, so count symbol. So first of all, we need to say, okay, right, the variable count, or for the interpolation, is gonna be equal. Let me put this in a new line. This is gonna automatically fix the format when I save. I have an extension for that. So, okay, but for now, let's put it like that. So count is gonna be, let's use the hex function, or this actually, what is this? Struct, once again. Doesn't say. I assume it's just a module that exposes some functions. So the first function is called encode, which we're gonna pass the public key, and it's gonna give us back a hexadecimal representation of the private key. So that's the first one. The second one is gonna be, then we want to see the size in bytes, right? So to calculate the size, we take the array, because public key right now, it's just an array of integers. As you can see, it's an array of unsigned 8-bit integers, and it has 33 elements, right? As we discussed in the previous video, in the theory part, a public key is stored using 33 bytes. So we use that, and we access the property length, which gives us the length of the array. Then we want to see the actual hexadecimal number, right? So hex is going to be equal. So we can just reuse this here. And just realizing that here that we don't want the actual encode. We just want the count. How many symbols do we have? So to do that, we need to first transform this value, or the return value from this function, to chars, which give us back an iterator, and then use the method, or the method count, so we can consume the iterator and know how many items do we have in this chars array. So first of all, we transform this into this chars, which gives us back an array where each element is stored as an item, and then we use the count method that consumes the iterator. In the case of the hex, it's just using this function straight up. And finally, we want to see the bytes, right? This is the raw representation, directly how it's probably stored in memory. So this is going to be equal to just simply the public key, nothing else. Let me see what else can we fix here. So if I save this, you can see it's deforms automatically. Let's try to run this to see how it works. Okay, so we run cargo run. So the first step is going to be to download all the libraries, and then it's going to create the binary and execute it for us. So it's take a little bit to get all those dependencies before starting the build process. And there you go. So it works. We have the public key has 66 symbols and 33 bytes. This is the hex of that public key. And to make it actually more explicit that it's a hex, we can use the formatting tool here, where we pass, I believe is in here in the hex, the colon X, if I'm not mistaken. Let's try again. And no, it's not implemented for, oh, I see. Okay. We can do it just manually like 0x, right? And that should work as well. Okay, so 0x, and then we have the whole hex. And these are the bytes that actually correlate with this hexadecimal number. So we have here 33 bytes. Okay, cool. So that's the public key. So if you recall, the very next step after getting the public key would be to start doing to get the public key hash, right? And the public key hash is going to be taking this public key, passing it through a SHA-256 algorithm, and then passing that again through the RIPE MD160 hashing algorithm. And that's going to give us the public key hash. So let's do that. For now, I'm just going to create then a new function where we can put that functionality. So we're going to call this function derive pkh. And this function is expected the public key, right? But it's expected, you just want to borrow the public key. It's not trying to own it. So we know that the public key is just an array of bytes, basically. And what we want to return is this public key hash. And we know, again, it's going to be an array of bytes. But because we want to transform or transfer ownership from the function to the main function that is going to call it, we need to use a vector. Okay, so we have the function signature defined, and in here we can just call it, right? So say, let me see. Let's try it. Okay, let pkh, and it's going to call that function derive pkh, and we want to pass the public key, but just borrow or pass a reference to it, right? And we should get back a vector. Okay, first step, we're gonna get the public key and pass it through the SHA-256 algorithm. And to be able to perform this hashing, we need to get another crate specialized for that, and that crate is SHA-2. So we go back to cargo.toml, get SHA-2, and the version right now it's 0.9.9.2. Now we can actually bring into scope the structs that we need. So we say SHA-2 and give me back the digest trait, and also give me the SHA-256 struct. We need this, both of this. And in our function now, then we can create the SHA-256, and this is going to be, to do that, we're going to use this struct and the associated function digest. This should be lower score. Yeah. All right. So this function, it is expecting just the public key to be passed, a reference to it. So again, a reference to the public key, and we have the hash. or at least the SHA-256 hash. Next step is to hash it again, but using the RIPE-MD160. And as you might guess, we need another library just for this type of hash. And that library, it's called the RIPE-MD160. And the version is 0.9.1. You can find all these crates or libraries in crates.io. Okay, so we have these new dependencies. So now we can bring to scope the things that we need, which in this case is, okay, let's go to the library and give me back this struct, the RIPE-MD160. Cool. And the way it works is a little bit different from this function signature or this associated function. It's a little more cumbersome, but we can use it anyway. So first of all, we use the struct and we call the associated function new. Right? And this is going to be our hasher. So let hasher. Cool. Next step is that we need to pass the previous hash that we created, this SHA-256, to the method update. So we say hasher update, and we pass our previous hash. But notice that this function, let me see. Oh, it's working fine. Okay. Cool. So we have updated the hasher, and now we just need to execute the hashing and just call finalize. So in this case, we say let pkh, and this is going to be equal to hasher.finalize. And that should give us back the actual public key hash that we are looking for. We can see that this is complaining. Why it is complaining? Let me check it for a moment. My actual code to see if it's implemented the same way. pkh drive utils. I'm just looking at a different window. Okay, I see. Right, so the part that we're missing is that this is expecting to have a vector, right? And let's see, the type that this function or this method is returning is called output self, and it's no idea. Yeah, this is a strange type. So I just want a simple reference, a simple slice. It will be easier to handle. So this is how we can create a reference, a slice that reference the same value. And from there, I can say, transform this to a vector. I believe this is the syntax. And that's it. We can just define it like this as an expression, which is just going to return the value. Or we can be explicit, say return, and then the semicolon. It's the same. Maybe just be explicit and use the return keyword. Okay, cool. So now let's see what's happening here. It's complaining because we missed the semicolon here, and now it's all good. So we can, okay, we have here an issue is because cannot borrow hasher as mutable as it is not declared as mutable, right? This is what I thought initially. This update is obviously just trying to update the internal state of the hasher. But in order to do that, we need to define this variable as mutable. So now it's allowed. All right, so let's do the same thing here, right? Let's say print to see the values, but now we're getting the public key hash, pkh. You're gonna get the same information, the symbol, the bytes, the hex, the bytes, whatever. Just in this case, we're gonna refer to the pkh on the public key. So basically replace all these references here. In this case, here, I believe I can use multiple cursors. I forgot how to do that. All right, there you go. pkh. And right. Okay, stop with the double cursor. Cool. So if this is working well, what we should see now is an array of bytes of 20 bytes actually, right? Because we know that RIPE-MD as an output, it gives you an array of 20 bytes. So let's verify. Let's run this. Let's clear the console and run again. Cargo run. Let's take a look. It's getting the new libraries that we added. And there you go. And to make it a little more readable, let's add more break lines in the middle. So let me add here at the beginning, and let me add one at the end as well. At the end, maybe at the beginning of every print might make sense. Let's try again. Okay, that's a little easier to read. So as you can see, the public key hash now is 40 symbols, 40 hex values, and 20 bytes, right? This is what we expected from the write MD. By the way, every time we run this function, we're gonna get different values just because this private key, it's using a random number provided by the OS. So it's always gonna be different. And right, so we have the hexadecimal number and we have the corresponding array of bytes down there. Good. The next step now will be to implement the base 58 check encoding as I showed you in the theory in the previous video. So let's see what we do now. All right, let's close this terminal for a moment and let's define a new function here. And let's call this function the base 58 check encode. And this function is gonna expect as a parameter the public key hash, which we know is just a slice of integers of 1 byte integer. And let's define the return type. Well, we know the return type is gonna be a string, right? This is the output as we discussed before. And the way that we're gonna use it is from main. For now, we're just gonna call base 58 check encode, passing the public key hash, a reference to it. So let me remove the return type for now, because otherwise we're gonna complain all the way that we are not returning that yet. Okay. So we know that if you recall the diagram that I showed you, first step is to add the version to prepend the version to the hexadecimal number. So let's create that. So we have a version variable, which is going to be of type it's going to be just 1 byte, right? And it's the value 0. That's it. So this is a semicolon. Okay, so only 1 byte, and I define this as an array because I know that the PKH is also an array, so I need to somehow concatenate the two. So we can come here and let's create the value that has the version plus the PKH, and that's gonna be the result of concatenating the version with the PKH and call concat. So yeah, I need to provide references here because we know that this is also a reference. I guess if I define here a reference as well, it's gonna work. No. All right. Sometimes you have to find the compiler in Rust to get it right. Cool. So we have now a number that contains the version first and then the PKH second. Next step would be, actually, before we move on, let's print that into the console, right? To verify that it's working correctly. So let's copy this code here. And now what we see here is going to be the version plus the public key hash, PKH. And what we're going to showcase is this variable. So it's going to come here, 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 and here. Okay, so let's take a look. We are calling the function, so we should be able to see it on the console, if I'm not mistaken. Let's go ahead and let's clear the console and run cargo run. Cool. So as you can see, we have, this is the new print. It has 21 bytes, right? Just one extra byte compared to the public key hash. And as you can see, it's just 0, right? Because we just added the original format for a wallet. Perfect. Next step would be to define the checksum for error detection. So let's go ahead, let's close here terminal and say, all right, let's create a checksum variable. And this is gonna be the double hash using SHA-256. So we know how to make a hash here, right? So we do it once, but we're gonna pass the version with the pkh, and we're gonna do it again. So let's copy this here, but we need to pass references to it. Let me see if I do this correctly. Digest, right? It expects a slice, basically. And then, why is this complaining? Oh, right, I need to turn this, well, I need the semicolon at the end, but I don't want the whole hash. What I really want is just the last 4 bytes. So we can get that easily just by, so the first 4 bytes. So we can just create a new slice this way, and then define, give me the first 4 bytes of this byte array. Okay, so we have the checksum. So now we can add the checksum at the end of this variable or this value that we're trying to construct. So let's call this new variable. It's going to be the version plus the pkh plus the checksum. And we do the same trick. We try to concatenate. In this case, we're going to concatenate this array with this one here, right? And call concat. And as before, this first one, let's use it as an array, as a reference to the array. Okay, seems to be working out. This is a immutable reference. This is also, this is a vector actually. So there's some hoisting, I guess, or in type inference happening, moving a vector to a slice. Cool. So now that we have this, we can print it out to see how it looks like and to compare with the other values. So now we have the version plus the public key hash plus the checksum. Okay, and so that means that what we want to print is this value here. Okay, let's run it and see what we get, if we get what we're expecting. Let's clear and run. Okay, so we have the version plus public key hash plus the checksum. And as we expected, it has 25 bytes because we added 4 bytes for the checksum. And if you compare, it's basically the same value, just with added hexadecimal numbers, in particular with 8 added hexadecimals, because they correspond to 4 new bytes. So this is the checksum, either as bytes or either as hex. Great. So we are moving along in the right direction. So finally, we need to implement the base 58 encoding to transform this hex into a string. And for that, we need another library. And that one is called, we close this here, it's called base 58. And its version right now is 0.1.0. Okay, back to our function. We can first bring into scope what we need from that crate or library. So base 58, give me back the 2 base 58 trait. And this is a trait that is gonna apply to every single array of integers, if I'm not mistaken. I think it's a blanket implementation, as they call it. Let's see if I see the description. Public trait to base 58. Right. Doesn't say exactly to which one apply, but I know for a fact that it's going to work for this array. Oh, there you have it. This is the implementation block, and it's going to apply for everything that is a slide of bytes. Cool. So we can go back here to our function, And let's say, so now that we have the version plus the public key hash plus the checksum, we can just call a new method that is called, it's going to be available because of the trait, to base 58. And that is not working. Why? Mismatch types, expect, blah, 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 found strict. Oh, okay. So because now we need to define the type. We know that what we want out of this function is a string, right? Which is exactly what this to base method is giving us back. So to make it explicit again, let's use a return and semicolon. All right. Let's now verify. So we need to bring this value back to our main function here, right? So now this is actually the wallet address that we're interested in. And we can print this out and keep comparing. So we paste here, and this is actually the wallet address, which is equal to the base 58 encode of the public key hash. Let's put it out. So it's going to be the version plus the pkh. Let's put a short format. Version plus the checksum, right? And we're gonna inspect the same information. So we're gonna pass here this variable and all these placeholders. Let's run it and compare once more. Okay, so our wallet address, so we know this is not, first of all, it is not a hexadecimal anymore, or is it? No, it's not, it's a string. So this doesn't make sense at all. We only want the bytes, let's see, count bytes, and the actual base 58 value, like the actual variable here. So I want to display, let me see, not the hex, but the byte. So here it's going to put the base 58, right? It's not hexadecimal. And that is just directly our variable. And in the case of bytes, because now this is a string, we can display that as bytes using this method. As bytes. Okay, let's just check if this is working. It's clear. Cargo run. And I see still the 0x. Okay, this doesn't make sense. It's just a string. Let's do it again. One more time. Okay. So we know now that it's this 34 bytes and it has 68 symbols. 68, that seems like a lot. I think something's wrong here, right? Because once again, we don't need to hex encode. We only need to know the size. So in this case, how do we count the symbols? Well, the symbol is going to be the same as the size of the array. So let me see how I did it before. Address chars count. Yeah, no, this doesn't make sense. So let's just put it here. This is in chars, which is the same as bytes. Well, let's put it here so it's explicit. So chars bytes, and this is this size. Yeah, it's gonna be the same variable. Anyway, I think I'm getting this a little too complicated, but because we know now that it has to be only 34 chars. You can call it manually. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 19. It's around 34. I'm not going to count it, but I know it's not 68, right? And these are all the associated bytes for this, for the char, for this array. I think I get something confused here, because given this encoding, I don't expect this to be only 1 byte per this is actually just should be 2 bytes or 5 bits, I believe. 5 bits. So we got the length in bytes. And yeah, no, I think this is correct. Okay, let's move on. So now we went from a public key to a wallet address using the base 58 check encoding. And now we can define the opposite process, right? If we have a wallet address, how can we extract the public key? So let's create a new function called base 58 decode or check decode. And in this case, we expect is to have a wallet address as the first parameter, which is going to be a reference to a string. And let's see, okay. And we call it from main. So we do the opposite here. So we're going to call base 58 check decode, and we pass a reference to our wallet address. There you go. Cool. So the first step will be to remove or to extract the checksum. First of all, we need to decode the string into a hexadecimal again using the base 58 decode. So we can go ahead and say, okay, give me the variable that has the version, the pkh, and the checksum. And that's going to be the wallet address, but apply the function from base 58, right? And this complains because no method name from base 58. That's because we need to import something else here, right? It's not only to base 58, it's also from base 58, I believe, I imagine. Yeah, okay. Where is it? Here, right? And as you can see, the result value of this function is of type result, which is an enum. I don't want to deal with those scenarios. I just want the okay or the good value. And for that, we can use a simple shortcut that is just unwrap. So it either gives me the right value or it's just gonna panic. I believe that's gonna happen. All right, so we have that. So now we can proceed to actually extract the checksum. And we know the checksum is the last 4 bytes of this value. So we're gonna get the version pkh checksum and say, oops, right, so let's see. So the checksum, it's equal to this, but I'm just gonna get the slice because I only want the last 4 bytes. And this is, so to get the last, we can do, so give me this variable and calculate the length, right? And we can actually make this into a variable itself. Let's call it length. And just pass it there. And now we can use this variable here. It's a little easier to read. We have the checksum, and also we can extract the other half, which is the version plus the pkh, which is the whole value except the last 4 bytes. So this is kind of the opposite operation here. So we want the version plus the pkh, and that's going to be this value again. But I just want a slice, and the slice is going to be, so the reference here, from length minus 4 until the end. I believe something is odd here. So the first 4 bytes, the checksum, right? No, what I actually want is the beginning except the last 4 bytes. and here is not length, because otherwise it's just the whole array, is the opposite. So length minus 4 until the end, right? So we have the first part and we have the second part. I believe this should be correct. Okay, so what do we do from here? So now that we have extracted the checksum, we need to recalculate the checksum from this value and to see if those actually match. So let's go here and do the derived checksum that we did it before. So it's just a matter of copying this double hashing that we did somewhere. Where is it? We did a double hashing, and this is here, right? We need to do the exact same thing, just with a different variable. Actually, it's the same name of the variable, the version pkh, right? So we have the derived checksum, and now we can compare both of them. I'm gonna compare them in hex because it makes more sense to compare strings than to compare just raw bytes. So we can use the same function hex. So I'm gonna say, okay, let me the hex value encode of, first of all, let's use this checksum here. Come on, copy, paste. Again, is a reference. I want to change ownership. If this is different than the derived or the hex encoded version of my derived checksum, then we know that we have a problem. Oops, it's supposed to be an ampersand. So if this happened, I just want to panic, which is like end execution. Something bad happened, and the error message is error checksum doesn't match, or checksum don't match, right? Just comparing both of them. Checksums don't match. Okay, it's a very simple error handling here, just fail and exit execution. So finally, to get the public key hash, we just need to remove now the very first byte, which is the version. So to do that, we create a new variable, pkh, and this is gonna be a slice, once again, of this one here. But I'm just interested in everything except the first byte. Cool. And now we're ready to return the value because now we found a pkh. So we know that the return here is going to be, again, an array of bytes. So we're going to use the type vector of unsigned integer of 8 bits, which is an array of bytes. And we say, okay, now we need to transform this slice or make a copy into a vector so we can handle ownership. Say return pkh to vec, if I'm not mistaken, and that's it. So now we can use it here. So let's call that, to not confuse it with the first variable called pkh, I'm just gonna call it derived pkh. So in theory, those two values should be the same, this one here and that one there. And just to verify, let's just print it and just take a look at those. And this is gonna be the derived pkh. Let's make it a little simple. Pkh. All right. So we're gonna have the same information. Just now replace the variables there and there, and let's take a look. Clear cargo run. So as expected, the derived pkh has 20 bytes. You can see here the hex and the bytes. And if we compare those, let's open here a little bit more. So we are looking at this one here, right? This number and this number, and they're actually the same, right? C7CBE29, C7CBE29. So we successfully were able to decode a wallet into a public key hash. So the only thing now pending is to show you how the error detection actually works. So let's make a quick change here, and we're gonna simulate that we made a typo, right? And this typo is basically we're gonna change the last character of the wallet address. Like, let's say that we made a mistake. Like, we're gonna first remove it, and then we're gonna add whatever, an A. So wallet address push. Let's push for an A. And then because we're mutating, we need to define here as mutation. So as you can see now, this is the typo. We should be able to trigger this error here, right? And this is the wallet trying to tell us, hey, don't go any further. You made a mistake. Don't try to send Bitcoin there. So let's see. Cargo run. And yes, there you have it. This is where the script, the binary panicked, and we say error checksums don't match, and nothing else get executed, right? We stop right after the base 58 encode. So with this, it covers pretty much all the topics that we covered in the presentation before. So we went from the public key to a public key hash to the wallet address, and then from a wallet address all the way back to the public key hash. And I show you how, if you make a typo, this base 58 encoding and decoding will be able to detect an error and prevent you from burning your Bitcoin. See you in another video.